Next, we consider a simple electric circuit. So we learned that charges by themselves can produce an electric field. And if there's an electric field present, that means that a charge placed in that electric field will experience a force. So it turns out we can also create an electric field in such a way that we have separated charge, positive and negative charge, and if we place any charge in the region of that separation of positive and negative charge, then it will experience a force. And so that separation of positive and negative charge is what we called electric potential or voltage. And this is something that we're all familiar with because we've changed the batteries in a flashlight or changed the battery in something or other, right, in our calculators or whatever. So voltage is basically something that comes from, a simple example would be a battery like we have here. And if you've ever looked closely at the battery, there will be a positive terminal and a negative terminal. And that positive and negative is basically just telling us that we have some separation of positive and negative charge on those terminals of that battery. And because there's separation of positive and negative charge, that means that we can create an electric field, and if we have an electric field, we can force charges to move because of that electric field. So let's talk a little bit about a battery first, and then we're going to talk about a simple circuit. So here is one simple circuit where I have a battery here in a battery holder. From each end of the battery, I have it connected to a bulb holder, and then the bulb is actually screwed in, and then here's another picture of that same type of situation. So let's look at a simulation that shows a battery. So in this particular picture, go make it a little bigger, we have the terminals of a battery, and right now the voltage is just 0, so it's set at 0. And I can change the voltage by taking electrons, because right now there's an equal number of electrons on either side, and then we have these charge carriers. And so inside the battery, there's a chemical reaction that will keep the charges separated, because remember, positive and negative charges want to attract one another. So if I change the voltage, then these charge carriers grab electrons from one side, move them to the other side. So now I have more electrons over on the right side, fewer electrons over here, so the left side is positive, the right side is negative, and I get this voltage, and I can grab even more. And they're going a little slower now because it's harder to separate and bring those electrons over, right? Because electrons want to repel one another. But I have now positive charge on one side and negative charge on the other. So if I connect this battery up and I get some, so I guess the best way to think about it is if I put a wire on this side that has electrons, those electrons are going to want to be repelled from the electrons that are on this side, and they're going to want to be attracted to the lack of electrons or the positive charge on the other side because of the fact that charges exert forces on one another. I can also change the polarity, so I'm going to just do it the other way, and I would have to move those electrons to the other side. So at some point it would be electrically neutral again when I have the same number of electrons. But then as the charge carriers grab those electrons chemically, there's chemical reaction going on, that's what the little people are, forcing the charges to stay separated and forcing those electrons to all be together over on that side. So a battery is essentially just something that has the separation of positive and negative charge, and whenever you have the separation of positive and negative charge, you have something called voltage. So if I want to build a very simple circuit, the things that I have to have are a voltage supply, and the voltage supply is going to be the pumping mechanism. It's going to allow charge to move through my circuit. I have to have conducting wire, or a conductor and conducting wire. I would need to have electrical current. I would have something called resistance in the circuit, and then I would probably want to have a switch. So when you turn your lights on, you flip the switch, that turns it on and off. The switch is actually optional. But the other things here are things that we really have to have in our simple circuit. So let's talk about those different items. So before we do that, we have to understand what a conductor is. So we can classify materials as either conductors or insulators. There's actually something called a semiconductor. We're not going to worry about that. But a conductor is basically any material that has free electrons that can easily flow through it when an electrical force acts on them. So if you apply a voltage to a conductor, those free electrons that are easy to move away from the negative side of the battery towards the positive side. So some good conductors of electricity are metals. So copper, aluminum, gold, silver, those are all pretty good conductors of electricity. Well, how do we know they're good conductors? So here, remember, we talked about the different elements, and we talked about the fact that the electrons are in orbits around the nucleus. And so one of the things that you should notice about copper, so here's copper, here's silver, and here's a representation for gold. One of the things that you should realize in these pictures is that for each one of these particular metals, there is only one electron in the outermost shell. So there's one electron each in the outermost shell. Here, here, and here. The outermost shell is called the valence electron, the valence shell, and that electron in that shell is called the valence electron. That electron is not very tightly bound to the nucleus because there's only one electron in that outer shell, and so it's very easy for that electron to break free from the atom, and those are called free electrons. So metals have very few electrons in the outermost shell, and those electrons can break free very easily. And so if I just had a chunk of copper at any given time, there would be electrons inside there that had broken free and are just moving around, grabbing onto one atom, leaving an atom, going to another atom, and so on. So conductors always have free electrons. Insulators, on the other hand, are materials that have very few free electrons that can flow through them. So their shells would be more tightly bound. They would only have one electron in the outermost shell. And so good insulators do not allow charge to move very freely through them. So we could ask a couple of questions. Is water a good conductor of electricity? And that's a really tough question. So pure water, H2O, is not a good conductor of electricity. However, impure water, which is water that comes out of your faucet, is a good conductor of electricity, right? So, like, for example, if you are swimming on a hot day and all of a sudden there's a thunderstorm, they always make you get out of the pool, right? Because of the fact that the water in the pool is actually a pretty good conductor of electricity. What makes it a good conductor of electricity are the impurities in the water. So the water is not just pure H2O. There's actually metals in the water and other things. There could be salts in the water because I have a salt swimming pool at home and so on. So pure water, H2O, is actually not a good conductor of electricity, but we very rarely see pure water in general. And so we have to be careful about how we think about that. How about air? Is air a good conductor of electricity? And the answer to that is no. In general, air is not a good conductor of electricity. It's actually a pretty good insulator. But even air can break down and conduct electricity. And if you think about it, you probably can think of an example of when air breaks down and conducts electricity. One obvious example is during a lightning storm. So in those circumstances, the earth is actually a pretty good conductor of electricity. The clouds accumulate charge, and then the surface of the earth also accumulates the opposite charge. So you have the separation of positive and negative charge, and what can happen is that the air that is between the clouds and the earth actually breaks down and starts conducting electricity, and electrons can jump and make it to the earth. So in general, air is not a good conductor of electricity, but even something that is not a good conductor of electricity under the right circumstances can break down and actually conduct electricity. So electrical current is something that we need to define. So electrical current is the flow of charged particles, specifically electrons, because electrons are always what moves. So it's the flow of these electrons in a conductor. So we could ask the question, what do we actually need in order to have electrical current? And we need to have conducting materials, so we have to have these free electrons that are able to move around. We have to have a pumping mechanism, which is our voltage supply. That's the separation of positive and negative charge, which is going to allow those charges to be pushed away from the negative side of the battery and attracted towards the positive side. We also have to have a complete circuit or a closed path for the electrons to flow through. So here's a simple picture of a battery, and with a positive side at the top, a negative side at the bottom, and here is a light bulb. That light bulb has a filament in it. It has a tip here and a base, and there is a wire that goes up and sort of connects through. Now the filament, when it gets enough electricity going through it, will glow and actually produce light. But I do have a complete circuit in this particular picture. So we could ask the question, so once I connect this up, this light bulb, this light bulb to this battery, you know, the light bulb glows. And so electrons are actually moving from the negative end of the battery. They're flowing through this circuit. They're going up through the filament, coming out, and then we have, you know, the positive side and so on. So where do these electrons that are flowing through here, producing electrical current, actually come from? And the answer is they come from the conducting wire itself. So here is a picture of copper. And inside the copper, you can see the atoms. So the larger circles or spheres here are the nucleus, and then the little blue spheres are actually the electrons. And so some of them are tied to the nucleus, but a lot of them are actually free to move around. And so what happens is that when you place the wire in the circuit, those electrons that are free, that are attached to the negative end of the battery, experience a force. And so there is this push of those electrons to move in a particular direction, in this case to the right. So the electrons, where do they come from? They come from the wire itself, being made of a conducting material, and there are free electrons that can just move around. Is the conducting wire electrically neutral or charged? Well, the wire itself is electrically neutral. So the wire is made up of atoms, and those atoms have protons, neutrons, electrons. But if you just have the piece of wire, there's the same number of protons as electrons. It's just that some of the electrons are free to move around, but at any given point in time, it's electrically neutral, same number of protons as electrons. This is a harder question. Does a single electron go all the way around the wire? So if I had an electron in the wire here at this end, does it go all the way around, pass up through, and then come back around? And the answer to that question is no. A single electron is not just zooming around this wire. What happens is you get a drift. So you've got these electrons which are randomly moving sort of all over the place in here, jumping from one atom to another, grabbing on, another one breaks free. But when you place this wire in a circuit, a complete circuit with a battery, there is an average drift. So even though the electrons are moving around, they start to sort of drift in one particular direction, and it's that drift velocity that we measure for the electric current. So a single electron is not just zooming around, and we're not counting those electrons. We're actually measuring how the electrons drift through that circuit. So the way that we define electric current is the rate at which charge passes through a given cross-sectional area of the wire. So the current, we use, the symbol for current is I. Charge is measured with a unit of Q, and it has units of coulombs, and then time is in seconds. So basically, if I had a piece of wire, and this wire is connected to a circuit so that it's a complete circuit, if I could stand here and I had a stopwatch and I measured the charge that passed through this particular cross-sectional area in a given amount of time, and I measured that charge and I put that charge in here and divided by the time, that would tell me the current through that particular circuit. Now, a good way to think about this is imagine that you are near a highway and you're standing alongside the highway, and the cars that are going by on a one lane, right? So you have cars that can only go in one direction, and you stand there and you measure how many cars go by in a given amount of time. If a lot of cars go by in a short amount of time, then that's a large flow of the cars, or in the case of electricity, that would be a large flow of electrical current, and so you would have a higher current value. So so the cars would represent the electrons, and then you're just counting how many go by in a given amount of time. There's two ways that we can describe electrical current. There's something called electron current versus conventional current. Electron current is actually the direction of the current flow that the electrons would go. That's actually what's going on in the circuit. Electrons are what are moving around the circuit. But traditionally, before there was a very good understanding of the fact that it's the electrons moving around, there was something called the conventional current direction, which is the flow of positive charge. So it's just the opposite. So if these are electrons, the electron flow would be to the right. Conventional flow would be the opposite direction, which would be to the left. We'll probably focus on drawing our pictures for the most part with the direction of the electrons, how the electrons are actually moving. There's also two different ways to describe current. There's direct current versus alternating current. Direct current is current that flows in one direction only, and that comes from something like a battery, right? So there's a positive end of a battery, there's a negative end of the battery. If you connect a wire up, the electrons are going to leave the negative end, go towards the positive end. There's only one direction that they can go. That's called DC. We also have alternating current, AC. In this particular case, the electrons oscillate to and fro about a fixed position. Alternating current is actually what you have when you plug into your outlet at home. Generators produce alternating current, alternators in your car, and so on. So there's advantages and disadvantages to both. Here's a picture of what the voltage would look like for DC over time. So the voltage would just be in one direction. It would say relatively constant. For alternating current, the voltage is actually changing direction. So sometimes everything above the axis is positive, everything below the axis is negative, and it's fluctuating from positive to negative, positive to negative. All devices resist the flow of electricity to some extent, even conductors. The more that they resist, the greater the resistance of that particular component is. And so we say that even a wire that's a good conductor of electricity does resist the flow of that electricity some. And there's some properties that can affect the resistance of a wire. This is something that you're going to see on the homework. But in general, we could see what happens. So as the length of a wire increases, what happens to the resistance? And so I'm going to go ahead and just describe the answers, but you can actually see this in the simulation and on the homework. So as you increase the length of the wire, the resistance of the wire, how much that wire is resisting the flow of electricity, actually increases. So you can imagine that the longer the wire is, the more the electrons can bump into atoms as it goes, and those electrons can slow down. As the area of the wire increases, what happens to the resistance? So if you have a larger cross-sectional area of wire, it actually reduces the resistance in the wire. So a very thick wire is going to have less resistance than a very tiny thin wire. That's going to have more resistance. So if you look out at the power lines, the lines that are going to carry your electricity are going to be pretty thick, right? They're pretty big around compared to the wires in your house. I don't know if you've ever seen wires in your house, but those types of wires are very small. The resistance also depends on something called the resistivity, and the resistivity is telling us what the wire is made of. So if it's made of copper, it's going to have a particular resistivity versus if it's made of silver versus if it's made of some composite of copper with other materials as well. So as the resistivity increases, the resistance also increases. So in general, conductors have pretty low resistivities. They do not resist the flow of electricity very much. Insulators have very high resistivities. They're going to resist the flow of electricity quite a lot. So the resistance of a wire is going to depend on a number of different quantities that make up that wire: length, cross-sectional area, and basically what the wire is made of. The units that we use for resistance are ohms, and I actually forgot to mention the units for current. So current has units of, is defined as charge that flows per unit time, so that's coulombs per second, and coulombs per second is actually defined as an amp. So current is measured in amps, voltage is measured in volts, and now we have resistance, which is measured in ohms. A lot of times we want to have a certain amount of current flowing through our circuit, and so we can manufacture something called resistors to regulate the current inside electrical devices like your computers or any type of electrical device that you can think of. So they are designed to have a very specific amount of resistance associated with them. So here's a picture of a number of different resistors, and they're color-coded. So the color code is going to tell you, how big the resistance value is. So even though all of these resistors look the same in terms of size, they do have different amounts of resistance to the flow of electricity. So the bigger the resistance, the more they will resist the flow of electricity in the circuit. What makes them different from one another is what they're made of. So although they look identical, the composite materials that make up these different components are different. The symbol that we use for a resistor is this kind of this jagged line, and we're going to start to see some pictures where we draw some simple circuits, and when we do that, that will be our symbol for a resistance value. So let's talk for a minute about the light bulb and what can actually affect the light bulb. So a light bulb actually has a filament inside of it. This is a very standard filament light bulb, right? So there's LED light bulbs now, there's halogen light bulbs. So we're looking at one that has a filament in it. So that filament has resistance associated with it. So one of the things you should notice about the filament is that it will often be sort of twisted. And the fact that it's twisted means that that's a pretty long section of that filament wire, right? So if I pulled and stretched that out, it would be long. So longer wire, more resistance. So the filament has quite a lot of resistance. It's also typically very, very thin. It's almost impossible. It's very hard to see those filaments in there. But they're very, very thin, small cross-sectional area, very large resistance again. So those filaments inside the light bulbs are going to have a very large resistance value. I wanted to just sort of point out something about the light bulb because one of the things that you're going to see in future lectures and in labs is how you're going to be asked sort of how the light bulb works. And so one of the things, let's look at this picture here. There is a tip down here, or electrical foot contact, the tip at the very bottom. There is a section that is the base of the wire, right here, the screw threads right here is called the base. And, or in this picture right here's the base and here's the tip. One of the things that you should notice is that there is a wire that connects the tip that goes all the way up through the filament and then comes back down and connects to the base. What is separating the base from the tip is an insulating material. So there's an insulator here and there's an insulator here that separates the tip from the base. And then inside the light bulb base, there's also more material that's an insulator. So everything on the base is connected to one end of the filament, and then the tip is connected to the other end of the filament. And that's going to allow for this light bulb, once it's screwed into the socket, to allow current to flow up through, maybe say from the tip, go up through the wire, through the filament, and then come out the side, and not be shorted out between the tip and the base. So if all of this was just a conductor, there would be nothing to force the electrical charge to go up through the filament and come out the side. So that insulator is actually very important. And the way that the light bulb is made is important so that you can actually get electricity to go up through the filament. The actual bulb itself, the glass bulb, is really just protective. It's just trying to protect the filaments inside from breaking.